So, as I think we all know by now, my name's Drew. I'm an educator here at Grok Academy, and I'm joined by Adrienne, who is also an educator. I'm New South Wales based, and Adrienne is WA based. So we are all over the country. And what we wanted to do today is we wanted to talk to you about the way that we implement the actual teaching of programming in our classrooms. Because it's too often that we just say, oh, we teach programming, but we don't often look at how we do that. And we don't often think of the role of research in the way that we implement programming in our classes. So we want to just dump on you a whole heap of resources, a whole heap of links to research for some of the ways that you can implement programming in your classroom. In particular, we're going to focus on a pedagogy called PRIMM, and we're going to focus on an activity called Parsons Problems or Parsons Puzzle. So when you're teaching your students to write their first program, I always started the same way. I'd get them to do a Hello World task. And I've done it in Grok, I've done it in Emacs, I've done it in a whole heap of IDEs, and I get them to go print Hello World. And it's a really common way that we introduce our first program to students, but it's also a really, really hard and complex way that we can have students write their first program.
Yes, so we do this at Grok as well. You know, whether or not we say hi Grok, it's the way that I first learned how to program, and chances are it's for you as well. But when we just ask students to do something like, you know, print Hello World, it might look easy, it might look like nice phasing for learning programming, but there's a lot actually going on that we can take for granted. They're being introduced to the concept of functions through the print function. There's the concept of output, where we're not actually printing anything, but we are outputting a string called Hello World. There's brackets or parentheses. We have our strings inside quotes, be they single or double, and they need to match on the other end. And it also requires a coding platform, whether or not that's the use of the Grok platform or IDLE or Atom or Thonny. And there can be a whole lot of cognitive overload with this. And in fact, the more that a student actually thinks about what's going on, the more that they can become overwhelmed about not understanding how something seemingly simple is in fact very complex. And they can then make misconceptions to try to understand what's going on. And these misconceptions can become embedded and harder to correct over time, particularly if a teacher doesn't know what these misconceptions are, which is quite likely when you have large classes. And students can get into a spiral of, I can't do this, thinking that it's more challenging. Yeah, when they see everything that's going on, with that feeling of being overwhelmed. And when we see our students, they will often come to us with a large range of programming abilities and experience. Some of them will have used Blockly or other visual programs like Scratch. Some are experienced programmers, some have not done any coding at all. Some students get more stuck when solving open-ended problems. Students are bringing in their problem-solving skills into coding. And then students also can struggle with very unhelpful syntax errors or runtime errors. For example, if we do something like Hello Barker College and leave off a quote, they're going to get the message that says EOL when scanning string literal and think what? So students with varying literacy levels can be challenged by this. And then if you've got the very common error of trying to concatenate a string and an integer in the second example, they'll get a runtime error at this point, being type error, unsupported operand type S. And it doesn't help students. So what we would like to do is introduce you to a more scaffolded approach in the rest of this presentation so that students don't get so overwhelmed. And we're trying to also build up resilience and for our first time coders as well during this process.
So as always, though, we do need to link to a syllabus, and it's as much as we like to go, oh, I wish I could teach programming and not have to link to the syllabus. We do. Fortunately, the idea of algorithms and implementing different algorithms is in both the technology mandatory and the new computing technology syllabus. And I want to note here that it says that when they design an algorithm or design, produce, and evaluate an algorithm, it doesn't say specifically what it is that we need them to do that in. So it doesn't say for stage 4, designs algorithms in a programming language. It says implements them in a general purpose programming language, but it doesn't say we have to design them in a programming language. And it's the same in stage 5 as well. They design, produce, and evaluate an algorithm. That's one part, and implement them in a general purpose and or object-oriented programming language. So the idea is here, we want to divorce the idea that you have to design an algorithm using an IDE or using some editor or using some language entirely. Because we need to scaffold the way that we implement this into a classroom. And the idea that students struggle with programming isn't new. There is a lot of research out there on students learning how to program, but it's focused more at a university level. There's not a lot out there for kindergarten through to year 12. There is some, and we'll show you some examples of that in a moment. But before I do that, I want to bring up this article here. It's called 10 Quick Tips for Teaching Programming. And I'm not going to go through all 10, they are all there, but I do want to draw on the top one. Remember that there is no geek gene, because I've even fallen into this trap as well, where I say, oh, that person knows how to program. They just know how to do it. They're the nerdy one, the geeky one, the programmer. The idea here is that programming is just another language, like we learn English or another language at home. So we don't just assume that you just pick up a language, we know you work at it. So now if we drop that assumption of there being a geek gene, now we need to have some strategies to give students that confidence to make them think that they have a geek gene. And there's 4 examples there. There's live coding, the idea that you get up in front of the class and you program in front of them, which can be daunting for teachers. And if you're not comfortable with it, your students aren't going to be comfortable with it. So we understand that. But it's important that they see how people do programming so that they can learn how to model themselves, and that's mistakes and all. Have students make predictions, and we're going to come back to that in a moment about actually having students think about what a program is going to do before it runs. Use pair programming, which is something that schools tend to be good at, if not completely correctly. And don't just code. In the same way that you don't just write in English, you don't just code. You need activities and things to do that aren't coding to support that. But some of the research we did want to show you is particularly done by the Raspberry Pi Foundation over in the UK. They just are really leading the way when it comes to school-based research for programming. And this one here, the Teaching Programming in Schools review by Waite and Sentence, is where we've drawn some of our inspiration for the programming pedagogy that we're going to talk about today, which is PRIMM. But that report talks about strategies, it talks about the context that you can use programming in, whether that's block-based or text-based or other different contexts, and also supporting learners as they go through that. But it is a long document, and we know that a lot of teachers are time poor, and I think the Raspberry Pi Foundation does as well. So what they've done is they've released these pedagogy quick reads, and we will link to all of these, but these are a double-sided A4 page that goes into the research behind how to implement and some of the effects of it for all these different pedagogical approaches, including PRIMM, which we're going to talk about today, and Python. So if there's one thing that you want to take away from this, that, hey, here's something that I can take back to my staff because you have over 300 Year 7 students, or that you yourself can take back to your own teaching, these would be it. But today we're going to focus on the PRIMM pedagogy. And PRIMM stands for Predict, Run, Investigate, Modify, and Make. And Adrian talked about that idea of scaffolding students, and that's what this really excels at. Because when a student loads up a program, whether it's one they've written themselves or the Hello World program that you've given them to type out, a student takes ownership of it. From the moment their finger touches a key, they go, this is mine, I'm on the hook for this. If this goes wrong, that's on me. It's because I'm not good enough. So what the PRIMM pedagogy tries to do is it tries to reduce some of that burden and that cognitive load on students by really almost hand-holding, but scaffolding is the term, really taking them through the different stages of learning different terminologies and different concepts. So the idea is that they go from not theirs all the way up to the make stage, which is creating a brand new task with all the skills that they've learned up until then, but we've scaffolded them up and then removed it away so that they can go by themselves. And it's really, really good because it goes into more than just coding. It goes into the idea that we're looking through different sections of code to read through it and understand exactly what's going on. As a teacher, though, it gives us a chance to look at and see what students are doing, where students are going right and really excelling, and where we might need to focus our intensity on as students are learning new concepts. And we'll show you what that might look like as we go through. And again, when we'll touch on it at the end, this isn't an assessment framework, but it does give us so much data about where our class is at that we can then take forward to inform our practice as we move forward. So the first stage is predict, and predict is exactly as it sounds. We want students to predict what they think the code does, but we don't want them to run the code. We don't want them to, they don't even need to be at a computer. All we want them to do is read through a snippet of code and go, what do I think this code does based on my own background, my own prior knowledge? At this stage, we don't want them to write. We just want them to be aware that this is something that we might be learning. And let me show you an example here. So let's say we're in year 7 and we're introducing a student to either Blockly or Python. The language isn't important here. It can be Scratch, it can be anything. The idea here is that all we want a student to do is go, what do you think this will do? Will this do, hey, will this print out, or what does print mean? Will this be, hey, word? Or somebody who might have program experience might go, it'll say, hey, you, or it might just say sentence. All you want a student to do is go, here's what I think this will do. And just by having them read through it and make that prediction is already forcing them to analyze the code in a way that is more meaningful to them than just typing it out. So we don't need technology, but this is where you can use your own background in programming, your own comfort levels, to focus on what you think where students might normally go wrong, or what you want them to draw out of it the most. So here's a snippet of code from a Python turtle program. I might want them to focus on at this stage, just looking to see what all these method names mean. What do you think color means? What do you think begin fill means? And I've asked this question to many teachers when I've run this at different conferences and things. And I said, if you don't know, that's okay. I actually really want you for this. What color is going to be printed? Is it going to be blue or green? What does that mean? And the idea is that a student has to go, okay, where does it say color? Oh, sky blue, spring green, which one would come first? We're reading through it. We haven't typed a line of code. We haven't run the code. We're just analyzing it to really start to understand where we're at now. And again, you don't have to do this individually. It's a great task for teams or pairs, or a higher confidence student and a lower confidence student. But after they write down that prediction, then they have to run it. And when they run the code, the most important thing to know here is that they do not type a single line out. When a student runs a snippet of code, they should be copying and pasting it, whether that means you give it to them through Google Classroom or Canvas or an email or a drive or however it's going to be. The most a student should have to do is copy it and paste it. Because again, if I give a student this sample of code, I've lost half the class because they're slow typers. They're way back here. Some are straight up ahead. Some person has realized that color is spelt with a U in Australia, and they've typed color with a U, and there's an error there, and they've checked out. So the idea here is that I don't care about what it is that a student's going to do. It's just run the program and then see whether my prediction was right. And this is where we can identify as what the class does and goes, you know what, all of my class realized that it was blue and green. Okay, so I now need to talk about parameters and the role of those, or they missed that area, or they did really well with that. the idea is that they just run the code, figure out if it went right or wrong, and then if they can, figure out why it went wrong. So again, that can just be a simple, oh, I didn't see the word you at the top, or I didn't know what word meant, or something like that. But that's on them.
Right, now we get...
Oh, sorry.
Got a question.
Yeah, do you mean wrong being not what they predicted?
Yeah, that's right. I mean, wrong as being not what they predicted. At this stage, they haven't learnt anything. Yeah. You would run this at the beginning of each individual sequence for a particular concept. And it's really important to say, I don't mind if your prediction was correct or incorrect. I just want you to see whether you know what it might do. So they might have to draw upon, and as you get further on in examples, they might have to draw upon use of variables. So you can see a set word to you up in our Blockly course there. They might draw upon that, or it's just, do you know from what you've already brought into this classroom, whether it's day 1 or day 203, can you predict what this is going to do before we begin? It's like a pre-assessment.
It's also ideal for doing in 2s or 3s as well, and give students some activities and they can work together on that. So the next stage is investigate. This is the final stage when the code doesn't belong to the students and the stakes aren't high. And they've already done the predict and run stage. And so we're adding in some more heavily scaffolded activities here, because it's at this stage that we're really starting to introduce the platform that the students are coding on as well. So and they might at this stage also be typing code and getting used to the IDE. And the investigate stage is where the bulk of the activities usually are. So the teacher again is providing the code, and in the form of copying and pasting, or a file that the students then import into the IDE. And the students are intentionally looking through it, and then they're changing key aspects of the code that's provided to see what happens. And this teacher can focus on misconceptions or problems that were identified during the run stage. So if a lot of students got one particular piece of terminology wrong, this is where you would address it. So the focus is shifting from what happens to why does it happen. And it's helpful for various concepts. We can use it for focusing on functions, loops, variables, lists, decisions, counting. It depends. We can use this at whatever stage the students are at. So I'd like to go back to a point that Drew raised briefly, is that PRIMM isn't a process that we go through in a course of work. It's a cycle that runs whenever we introduce new concepts. So it can be used for students at more advanced or at very introductory levels as well. So in these particular examples, so this does show this, that you can use it at different complexity levels and in different languages. We can use it with single lines and conditions, like we're testing here if the flavour is chocolate, and we can look at what happens if they change chocolate, or if they change the variable called flavour. And we can use even single lines to help students understand the concept of a variable. We can use it with blocks of code to help students understand what happens when they put a variable in a string, again in Blockly. Or we can use it when we're introducing functions later in text-based programming, and we get students to start to investigate what might be happening if they change the name of a function, but they don't change the function that's called, or if they unindent parts of the code in the function. This again, at this point, the tasks are highly scaffolded. They can you could see what happens if they remove the count variable, and or they can trace, they can put in an extra statement and print statement of the count variable and see what's happening to the value of count when on each iteration of the while loop. So what else? They can see what happens if they change the variable of sides and look at indenting. They can deliberately break the program at this point and see what happens. So this is, at this point, they're getting more familiar with the IDE that they happen to be using, and they're breaking code that they didn't write to see what happens. So they're starting to learn the concept of debugging and some of those threatening messages that we saw earlier on with the EOL literal and what happens if they concatenate a string and a number. And they can then see or get familiar with the kind of error messages and start to learn what they mean and what they need to do to fix them. Okay. Oh yeah, Parsons puzzles. Okay, so we're going to talk about Parsons puzzles and how they're very, very helpful in the investigate stage as well. Okay. So Parsons puzzles can be really helpful for understanding code structure, and they can be a very useful modeling tool for how to write logical, helpful code. You can use them in Scratch or Blockly or other block-based languages, or in text-based languages. And they can also be used for formative and summative assessment. Again, we're reducing the cognitive load by supplying them with the code, and they can be useful to be done in pairs or threes together, so with pair programming. All right, so here's with Scratch, it's really easy to do a Parsons puzzle because, or Blockly, because we just pull the blocks apart and we tell students what the code's supposed to do. We give them the desired output, and the students then have to figure out where all the bits go. So that's, and we'll give you some examples of in Scratch. There's one later, so we'll give you that link later. And it's also easy to share puzzles in Scratch, so that's easy to do. And Python example. So we saw the other ones earlier where you would just drag the lines on in Python in the required order to solve a particular coding issue. You can also add distractors where a statement that doesn't actually belong is added to the list of options, and students then need to decide which one's got the right syntax here, so students can get more familiar with syntax at the same time. Or there's also the faded Parsons puzzles where we can ask students to fill in the blanks, and we may or may not give them all the options that go into those particular blanks for another level of scaffolding. Okay. Yeah, so you can build your own fairly easily, and there's some tools that are down the bottom of that particular slide about how to make your own, and we'll give you those links. And there's some that has been supplied as well, some examples for students, and there's a worksheet as well where students can get familiar with using Parsons puzzles in Scratch. And you don't actually even need to use a computer for this. They can just be put in, bits of paper and given for students to do together in pairs to go and put code together. So it's useful for simple tasks, and it's also very useful for understanding or even object-oriented programming and functions to put the code together for more advanced students as well.
Yeah, the idea is we want to divorce the idea of syntax from the actual code running. So you don't have to, with a parsing problem, you don't have to type anything unless you want to use some of those stated parsing puzzles. It just gets the idea of them focusing on structure rather than syntax itself, and then using their own understanding of that. So that's why it's really good in that investigate phase as an activity that you can run. But once we've sort of gone through our code snippets and our scaffolded activities, we want to begin to pull the rug out from under students, just a little bit at a time. And we want now, rather than give them the tasks that we want them to do with a sample of code, we're now going to start to introduce a little bit of independence in the modify stage. And with modify, what we want to do is we want them to, again, continue to make changes, continue with that idea of exploration of code and exploration of all the different little intricacies that make up a computer program. But we're going to ask them, we're going to give them more of a goal and less of how to get there. So the idea is that we want to start simple and move to complex. And there's some examples there, but I want to jump back because I really like showing this through line of one particular program as we go forward. But I'm going to come back to this Python turtle problem here. And we've now gone through all these different stages. As Adrienne said before, if, say, I wanted to focus on indenting for while loops and to show that loops require a one-step indentation, now what I'm going to do is I'm going to ask them to do slightly different things. So we'll start simple and we'll say, again, focusing on that color. This time what I'd like you to do is I'd like you to focus on changing the color of the shape. We talked about sky blue and green. What happens now if I want to change the color to red, or I want to change it to black or pink or tan? How do you think I'd do that? They can draw upon their knowledge that they did in the investigate phase, but the idea is that they're starting to do things more independently. Then they jump up a little bit further, and as they do that, and again, this is where we're doing it in pairs if we still want to, and again, your context is your context. But the idea is that as they progress through these different modification stages, they're getting harder and harder. So my students who are really excelling and who might have already done this already, they're going to breeze through these hopefully quickly and get down to the 8th task here, include a third shape, 25 steps of this second shape, so that I can see that you know what forward means and what this parameter here might mean to change it to 25, and to show that I might need 2 separate loops for 2 separate shapes, right? There's still a lot that we're doing in here, but a lot of it can be copy and pasted from our investigate phase and applied into that new context. So students aren't required to do all 8 stages, but they are required to start simple and work hard. A student who is less capable might only get up to making it a shape with 4 sides because I want to see that you can adjust this variable here because you know what a variable does for the final product. Whereas a more confident student might do all these and might do them in the same amount of time. So the idea is that we've pulled it out now, and now hopefully with the idea of reading through the code and doing these structured activities through the code, they're now at the stage where they might feel confident enough that they can apply it into an entirely new context. So they're going to make something new. This is where your normal assessment task might be. I want you to create a program that does this. I want you to create a program that asks for an input and asks them to make a calculator where they pick 1 for addition, 2 for subtraction, whatever the task is going to be based off what you've learned up until then. But it's applying it in a new way. And it's hard in schools, but they need time to be able to explore the tasks that you've asked them to do, but also relate back to some of that scaffolding that we gave them earlier so that they don't feel it on their own. The idea here is that they're going to be able to understand what they've done and how it applies into this new problem. So going back to our Python turtle example, this is where they're going to do things like make a brand new shape entirely that might have a set of criteria, a program might allow for fill color, line color, shapes and sides, but that's all I tell them. I don't tell them how many shapes, how many internal angles they need. That's up to them. They might have to do all these little bits of different pieces that show, oh, I know a Python command that I might use, and the idea of turning right and moving forward and moving backwards and pen up, pen down, and that they're going to produce their final solution in something like Adrian said, some IDE that they've been experiencing with, because too often we just go, use this and type this in here, and we don't really give you time to explore how this works. So that's why it also benefits students having this exploration time in these different phases, and that might be 1 lesson, 2 lessons, 5 lessons, 10 lessons, however many it's going to be for the complexity of the task. But giving them time to do it builds their confidence so that when they come to a make part, they're more inclined to go off and apply this knowledge that they've learned over the last few lessons. But as Adrian said, it's really easy for a teacher to go, oh, this is a great assessment thing. And parts of it are. But the idea is that PRIMM is a pedagogy in the same way that the pedagogy isn't an assessment task in other subjects. The way that we teach programming to our students isn't an assessment. It's how we build their learning. So it's a learning process. However, we can use these not so much as a summative assessment, but more as formative. I can see where my class is at this very moment in time from how many students got their prediction correct or incorrect. And I can see where they've sort of come to. The only part that can really be used as a bit of a summative assessment might be their make task. Their final task can be summative. But again, that depends on how many lessons you've spent building up on this, on the complexity. One of the bits though that can be used, yeah, go. Sorry, you had a question?
No, I think that was fine.
Cool, not a worry. So Parsons puzzles though can be an assessment tool. You can give a student a Parsons puzzle and say, hey, we've been learning a lot on this idea of casting into strings into integers and doubling back. And I've got a little Parsons puzzle here that I'd just love for you to do for me and assemble in the correct order. And that can be a really good assessment tool that, again, they've had familiarity with in their investigation phase, so they know how the task is going to work. Like students know how a close passage works. But it really does give you an outline of, oh, do you know what? This student was able to correctly indent their loops enough. I can see that they know the structure of a loop, whether that's a while loop or a for loop or, some other programming concept. It's really good because it works well both within that PRIMM framework, that pedagogy, and also summatively as I have this piece of data that I can show. So we had about 45 minutes, and I think we've hit that. So is there anything that we can touch on or any questions that this might have raised for you that we could help you with now while we're here?
I'll just go around the room. Drew, Darren, did you have a comment or a question?
No, but I want you to know that I'm wrestling with the application of code into a design situation. Like in the stage 4 technology syllabus, there's a requirement, particularly for the other units of work, that students apply a design process. And even as they move through the senior years, they're trying to identify genuine needs and opportunities. Now, I understand that coding is broad and complex and time consuming, and that you need to spend a significant amount of time, I guess, laying some foundations. But it would be also still nice for the students to understand those connections to how coding enables, I guess, design solutions to be brought about. And it quite often happens that they're kept separate, and that might be a necessity for clarity to the student, but it would still be purposeful, or at least useful for them to understand that, this is going to be enabling. And I mean, we've got a little project which we do in Year 7 where they can change words on a screen and change the lights, and I guess that's part of the way there. So I'm just letting you know that in my mind I'm trying to grapple with how they understand that from a bigger picture as well. And
you've hit the nail on the head where projects are the way to do that. It's we too often go, a student, as much as the syllabus says otherwise, it is oftentimes that a student comes into year 7 with very limited programming knowledge, right? And we start to build them up there. But in the same breath, we have them learning a language, normally English, from kindergarten, and they have years of that. They have years of reading and writing even before school, in school, and post school. So what we need to do is we need to try and combine a lot of that. And one of the tasks that I always ran in my school, because I taught out at a central school out in rural New South Wales, was a smart garden. Because too often we'd say, "Oh, this programming doesn't matter to me. I'm going to be working on Dad's farm," or whatever it's going to be. And one of the tasks that we ran, and Grok does have a course that teaches kids through it, but the idea is that they had to just purely monitor a water, the moisture level of a water. You know, it can even just be a cup of water with a little plant in it. And they use coding to continually check, continually monitor. I'm still getting a lot of those core concepts like looping to continuously be checking water quality, or soil quality, I should say. And the idea is that as you said, they're seeing that programming applied in a new way, which for them was agriculture based. So it's that idea of finding projects that appeal to your students and your context, which is, I'm making it sound like it's something simple, and it's really not. But finding projects that go, okay, well, let's introduce this into something that you already know, but let's do something related to programming with it. I've even gone into a year 5 classroom and used programming to, they attach coins to each individual bit in a little board, a little microcontroller. And as they touch the coin, it adds the coins up. And the idea that they're going to be continuously monitoring that. So it's a pretty long-winded way of me saying, but the idea is we really need to focus on projects that give students that real context. That's more than just video games, because that's the other one that a lot of teachers fall into, because students want them to go, well, I want to be a gamer, but it's hard to see the physical impact of that in a class, outside of a classroom, I should say.
Thank you, Drew. Kim, did you have a comment or a question?
No.
No? Thank you. And the other, we've got Tim. Do you have a question or a comment?
No, I'm just on the learning train. So
Yeah.
This will be good. Just being able to bring that across into the classroom will be the challenge.
Yes.
We are looking to set up, just back onto the link with the projects, and I think that's the better way to do it as well, particularly for engagement and clarity and understanding and whatever. But we do have a technical aid here, and we are looking to try and set up access where students can come in their class and look at a whole range of different sensors, and then and look at the coding that can then be utilised to change those sensors or get a response from those sensors, so they can understand, I guess, more tangible links.
Yes.
Yep.
So have you got microbits, or have you explored the microbits?
Yeah, we have explored microbits, and we do use microbits, so that's more than likely the way we will go. But what we don't have, and we've only just have access to this year, is a space to set all this up. So, like, we have 5 sensors, but there's probably 50 sensors out there you can go and purchase on the market, from flex sensors to movement sensors to light sensors and whatnot.
Yes.
And I think that opens up an enormous opportunity if students can see the scope and application of that side of things and then understand that it's linked to coding.
Yeah, and one of the other ones that you could do is the idea of building that space into a smart space. And that can start one at a time of, let's focus on, as a class, one particular aspect, just even as simple as a light switch, and go, okay, well, how do the streetlights automatically turn on? Let's see if we can replicate that in the classroom. What do we need to have happened for our lights to turn on? Well, we need it to be dark. Okay, well, how are we going to find that? Well, we need something to measure how dark it is. Let's see if we can find that sensor and then apply it. And I think that's something that the department is also recognizing, or NESA is also recognizing with the new syllabus being mechatronics, having a mechatronics component to it. So they're recognizing that the idea of automation and mechatronics is something that is going to come into play, and it's something that helps ground students. So having a space is really good for that, whether they can set up a tangible product, even if that gets disassembled at the end of the lesson or every couple of lessons, that they can experiment with. Because the idea is that we don't give students enough time to experiment with what can go right. and what can go wrong, which is, as any programmer knows, you're going to get it wrong 58 times before you get it right on the 59th. But with our time constraints and with our space constraints and with our syllabus constraints, and we're going, no, you need to go correct, because I have all this stuff that I need to teach you so that you can continue to build without really getting into, well, how does it do this?
Yeah. If I can add as well, when we just go around the room, when we ask our students, what are some examples of tech that you have, smart tech? I'm always amazed at how much they have. You know, they know their dad can keep an eye on the pool pH level on his mobile phone. They know that, you know, mom can check the irrigation system on her mobile phone. And then we ask them, well, this smartwatch you've got on, how does that know your steps? So most of them like to find out, oh, really? This is that same thing. This is that same tech, and it helps to kind of make it give it some relevance and context. So
agree,
yeah.
Because it's so, digital technologies and coding and programming is so abstract that it's so hard for students who aren't exposed to it at all to go, hey, here's how this works. And that is our main goal as educators, is to say, well, here's the relevance of it. Here's that classic line, oh, I'm never going to use this outside of school. And that might be correct for some subjects, but for computers, it's really not these days. You know, even down to, again, my agriculture context. A lot of what farmers were doing 20 years ago is now done by drones and monitoring, you know, different environmental conditions and checking fence boundaries with a drone rather than sending a guy out on a ute to drive the entire length of the property. So it's all about going, no, this is something that's going to stick with you your whole life, and here's how it's going to work. Wonderful. Have a lovely afternoon, everyone.
Thanks. Bye-bye.
Bye.